This week we're going to focus on small sample hypothesis test. Last week we went over sort of the theory and terminology of hypothesis testing. And as an example, we used a large sample. And we'll get into more large samples next week. But for this week, I want to focus on small sample methods. In this example 2a, a sample of n equals 3 patients, proportion cured by the new drug, p hat 2 out of 3 or 0.67. It is known that the proportion cured by the old drug, p0, is 0.6. We want to test the following hypotheses. H naught, p equal 0.6, new drug is not better than the old, versus HA, p is greater than 0.6, new drug is better than the old. We want to check that n times p0 is at least 10. So 3 times 0.6 is 1.8, greater than or equal to 10, question mark, and that's a no. Also, n times 1 minus p0, 3 times 0.4 is 1.2, greater than or equal to 10, and that's a no. So that means we can't use the z-table, and we'll have to compute the exact probabilities. And we will do that using a tree showing the 8 possible outcomes. And we'll set up the tree as if the null hypothesis is true. Okay, so so here's our tree. First patient is either cured or not. If H naught is true, they have a 0.6 chance of being cured, a 0.4 chance of being not. The second patient is also either cured or not, but with 2 patients together, now we have 4 possibilities. We have cured, 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 not cured, cured, and not. So both patients are cured. First patient cured, the second one not. First person not cured, the second patient is cured, and neither is cured. So we have 4 possible outcomes. Each time you add a patient, you double the number of outcomes. So with 3 patients, now we have 8 possible outcomes. And we're going to multiply across each path. We'll have 8 paths to this tree. So the cured, cured, cured path, you multiply as you go along, 0.6, 10.6, 10.6, is 0.216. That'd be cured, cured, cured. Next path, cured, cured, and then not cured. Again, multiply as you go along that path, 0.6, 10.6, 10.4, 0.144. It's cured, cured, not. And so forth. So we have the cured, not cured, and then cured. We're interested in the paths where at least 2 out of 3 were cured. So in our sample, 2 out of 3 were cured. So what is the chance of that happening if the new drug is no better than the old? So those are I put those paths in red here, where you have at least 2 out of 3 were cured. And so the paths in red are the ones we want to add up. If you add these up, we get a total probability of 0.648. So if H naught is true, then there's a 0.648 chance that at least 2 out of the 3 patients would be cured. So that's it's over 60% chance. So if the weather people say there's a 60% chance of rain, I'm probably going to carry an umbrella, right? It's more likely than not. So there's a good chance that they would have gotten 2 out of 3 cured, even if the new drug is not better than the old. So the 0.648 is more than our desired level of doubt, which is 0.05. That means we failed to reject H naught. The sample does not provide enough evidence to say the new drug is better than the old. And then if we have some adjectives for interpreting p-values. And see if I have that. I don't know if I have. See if I have that here handy. I do have a chart for interpreting p-values. So that, anyway, p-value that small provides little evidence that the new drug is better. See if I have, yeah. This chart is kind of hard to read. The printing didn't come out very good. Boy, this one's better. Okay, so yeah, the p-value between 0.1 and 1 provides little evidence that the new drug is better. Okay, so I think I have some okay, so I'm going to do another example, example 2b. We're going to redo example 2a if the sample size n is equal to 1 and p hat is 1 out of 1. So the 1 out of 1 were cured. So the proportion cured was 1 out of 1. So we had one patient and that patient was cured. So we want to know, does that provide sufficient evidence to conclude that the new drug is better than the old? Okay. For hypotheses, p equal 0.6, new drug is not better than the old, versus p greater than 0.6, the new drug is better than the old. Again, we want to check the n times p0 it should be at least 10. So n is 1 times 0.6 is 0.6, bigger than or equal to 10, question mark, and that's a no. We also do 1 times 1 minus p0. That's going to be 1 times 0.4, 0.4, and that's also less than or equal to 10. Okay, so we can't use the z-table, we have to use a tree. This tree, there's only one patient, and either the patient was cured or not. So this is a small tree. Either the patient was cured or not. We only have, and there's only one path where the patient was cured. So that's going to be this path here in red. Its probability is 0.6. So the p-value is going to be 0.6. That's more than our desired level of delta alpha. Again, we failed to reject H0. The sample does not provide enough evidence to say the new drug is better than the old. And again, if you consult that chart, p-value is 0.6, is between 0.1 and 1, it provides little evidence. It might be that the new drug is better, but that could have easily happened by chance to get a p-value of 1 out of 1. Example 3a, we have a sample of n equal 10 light bulbs, and the proportion of defectives, p hat, 0 out of 10 or 0. In order to meet industry standards, the proportion of defectives has to be less than 0.1. Okay, so the hypotheses will have H0 P is equal to 0.1. Company does not meet the standards, versus HA P is less than 0.1. Company does meet the standards. First step. I check that n times p0 is that's equal to 10 times 0.1. And that's going to be 10 times 0.1 is 1, and that's not greater than or equal to 10. So that's a no. And then n times 1 minus p0, it's 10 times 0.9 is 9, that's not greater than or equal to 10. So that means that we can't use the z-table, and we'll have to use a tree. The full tree would have over 1,000 paths, because each time you add a light bulb, the number of paths doubles. So if you sample 2 light bulbs, if you sample 1 light bulb, there's only 2 paths. Either the light bulb is defective or it's good. But if you check 2 light bulbs, now you have 4 possibilities. We have defective, 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 good, good, defective, good, good. So each time you add a light bulb, the number of paths doubles. So the full tree would have over 1,000 paths. It's not going to be practical. But we really only need 1 path. There's only 1 path where all 10 are good. So we can just make the 1 path. I did this vertically to make it fit on the paper. But we had all 10 light bulbs are good. So you want to multiply along this path here, 0.9, 10.9, 10.9, 10.9, 10.9, etc. And we get a p-value of 0.3486 something, which rounds to 0.35. So there's a 35% chance of no defectives, even if the company does not meet the standard. So this p-value 0.35 is more than alpha, which is 0.05. That means we failed to reject H0. The sample does not provide enough evidence to say the company meets the standard. So based on this sample, maybe this company meets the standard, maybe they don't. We don't know. And p-value 0.35, anything between 0.1 and 1. The adjective is going to be little, provides little evidence. 1.1 and 1. Okay. Example 3a. We do this example if the sample size was 1. Usually you're not going to sample one light bulb. You're going to sample more than that. But I just some of the WebAssign questions have sample sizes of 1, which was confusing people. So I wanted to include some of those. So again, we want to know, we want to test H0. P equal 0.1, company does not meet the standard, versus HA, P is less than 0.1, company does meet the standard. Again, check that n times P0 is at least 10, and that's going to be a no. 1 times 0.1 is 0.1, not bigger than 10. N times 1 minus P0, 1 times 0.9 is 0.9, also not bigger than 10. So again, we can't use the z-table, and we have to use a tree. And this tree, there's only 1 light bulb, so there's only going to be 2 paths. Either the light bulb is defective or it's good, and there's a 0.1 chance of being defective if H0 is true, and then 1 minus 0.1 is 0.9, a 0.9 chance of being good if H0 is true. So there's only 1 path that we're interested in, and that's the good light bulb path, and that has a 0.9 chance of happening even if H0 is true. So that's going to be our p-value, which is more than our desired level of doubt at 0.05. Again, we failed to reject H0. The 1 light bulb is not going to provide enough evidence. Example 4, sample of n equals 4 tosses of a coin. The proportion of heads, p hat, is 3 out of 4, whereas decimal 0.75. If the coin is evenly weighted or fair, the proportion of heads in the long run should be 0.5. So either it's heads or tails, and if heads and tails are equally likely, the probability is going to be of getting a head is going to be 0.5. Okay, so we test H0, P equal 0.5. Coin is evenly weighted. versus p not equal to 0.5. The coin is not equally weighted. So this is what's called a two-sided alternative. So when we're testing light bulbs, we had a left-tailed test here. We had a less than HA was P is less than 0.1. That's a left-tailed test. We're only interested in determining whether the number of defectives is small. And for the example with the drug, that was a right-tailed test. We're only interested in the new drug if the cure rate is higher than that of the old drug. So this is a right-tailed test. This is a two-tailed test here. A coin is going to be unevenly weighted if there's either more heads than tails or fewer heads than tails. Either way, it's not evenly weighted. So we want to include both extremes when we make our tree. So this is not the full tree. The full tree would have 16 paths, but I only did the paths where you had at least 3 heads or at least 3 tails. So you wanted both extremes here. So our p hat was 3 out of 4 heads. So we want the probability of 3 or more heads or 3 or more tails because it's a two-sided test. So these are the paths. We have all 4 heads. And I didn't put the probabilities here because they're all the same. They're probability of head. If the coin is evenly weighted, then the probability of head is 0.5. The probability of a tail is 0.5. So we set up the tree as if H0 is true. So because the probabilities are all going to be 0.5, I didn't actually write those in. But the probability of so the probability of each path is going to be the same. It's 0.5, 10.5, 10.5, 10.5, 0.025. And there are 10 paths where at least 3, with at least 3 heads or at least 3 tails. So these are the 10 paths. So 10 times 0.0625 is 0.625. And so the probability of getting a result this extreme from an evenly weighted coin is 0.625. So that could easily have happened. It's certainly more than our desired level of doubt alpha, 0.05. That means we failed to reject H0. Sample does not provide enough evidence to say the coin is unevenly weighted. And then if you look again at this chart here, the p-value of 0.6 is between 0.1 and 1. That sample provides little evidence that the coin is unevenly weighted. Example 4b, here we redo this, except now the sample size is 1, and p hat, proportion of heads, 1 out of 1, or 1. So the hypotheses are the same. H0, p equal 0.5, coin is evenly weighted, versus HA, p not equal to 0.5, coin is not evenly weighted. We checked n times p0, is that equal to greater than or equal to 10, and that's a no. 1 times 0.5 is 0.5. Likewise, n times 1 minus p0, 0.5, not greater than or equal to 10. So that means we can't use the z-table, and we'll have to use the tree. This tree only has 2 paths. If you flip a coin once, either you have a head or tail. Those are the only 2 possibilities. And our p hat was 1 out of 1 head. So this is the result that happened with the head. But because it's a 2-sided test, we want to include both extremes. So we want to add the 0.5 plus the 0.5 is 1. So the p-value is going to be 1. So p-value of 1, that provides no evidence against H0. Okay. No evidence that the coin is unevenly weighted. Okay, so here's some other comments in the appendix. Probability of making type 1 error is called the level of significance, but I like to call it the level of doubt. It is the probability of rejecting H0 when H0 is true. p-value is the actual level of significance or doubt based on the data. A lower p-value provides stronger evidence for rejecting H naught. The Greek letter alpha is the maximum desired level of significance or level of doubt. It is set by the researcher, and typically alpha is 0.05. We'll usually use alpha equal 0.05. If the exercises and web signs say something else, then use whatever value they give you. So they might give you a different value, but 0.05 is probably the most commonly used value. And if the p-value is less than alpha, then we reject H naught. Some researchers don't set a value for alpha. They simply report the p-value and leave it up to the reader to interpret the p-value. And then again, here's the chart for the p-values. P-value equal 1, no evidence against H naught. P-value between 0.1 and 1, little evidence against H naught, and so forth. Okay, some more comments about setting up hypotheses. Usually the goal is to reject H naught and provide evidence that HA is true. Thus we're looking for evidence that the new drug is better, or that the number of defective light bulbs is small, or that the coin is unevenly weighted. When there is not enough evidence to suggest H naught, to reject H naught, you may occasionally see the expression accept H naught because of the awkwardness of the double negative, and the expression failed to reject H naught. So you'll see that, but technically that's not the correct language to use. Technically we reject HO and accept HA, or we fail to reject H naught and we don't know. But we technically shouldn't be accepting H naught. Okay. So just the cure rate of the new drug, if you're going back to example 2a, cure rate of the new drug p hat is 0.67. It was slightly higher than the known 0.6 cure rate of the old drug. So the sample did provide a little bit of evidence that the new drug is better, but because of the small sample size, there was a 64.8% that this could have happened by chance, even if the new drug was not better. So that's something to keep in mind. That so anyway, the data is not conclusive. We don't know whether the new drug is better or not. It might be the larger sample size would provide stronger evidence. So technically the correct way to express the conclusion is that we fail to reject H naught, even though that language is awkward because of the double negative. And that concludes this presentation.